Welcome to Manufacturing Processes, Machining and Machine Tools lectures by Professor Joyjeet Ghose. This is the 17th lecture of a series of lectures. This lecture will be on grinding, part 1. He will be discussing about the grinding, physical model of a grinding wheel, grinding, and chip production, grinding wheel shapes, comparison of grinding and milling, grinding wheels variables like abrasives, types of bonds, grain size, grade and structure, specification of grinding wheel, selection of grinding wheel, mechanism of grinding process, cutting forces in grinding, specific energy in grinding, calculation of grinding force, wheel wear, grinding ratio, grinding wheel mounting, grinding wheel balancing, grinding wheel glazing and loading and grinding wheel dressing and truing. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to this lecture. In this lecture, we will be discussing about grinding. This lecture is actually divided into two parts. In today's lecture, we will be discussing about the grinding wheels and the grinding mechanisms. And in the next lecture, this is part 2 lecture, we will be discussing about the grinding processes. So let's start with the discussions. We will discuss what is grinding first. We'll have a general idea about what is the grinding process. You can see there is a wheel and there are abrasives which are attached to a grinding wheel which is rotated against the rotating cylindrical workpiece in this particular case, and you can see the grinding abrasives are having negative rake angle and are removing material from the workpiece in minute quantities. So basically grinding is used when there is a precise dimensional requirement, when you want to remove, when you want to obtain a very good surface finish, when you want to remove a small volume of material, and when you want to machine hard surfaces, when the force requirement is low and very thin layer of materials are to be removed. In grinding, basically what happens is the rotating wheel which has number of abrasives maybe at the periphery or maybe at the face, just like a milling machine and milling wheel rather. So these abrasives comes in contact with the workpiece and removes the metal or material from the workpiece in minute quantities. Now this grinding abrasives have negative edges and they are rotated at a very high speed. The temperature that generates is also very high. The specific energy that is required in grinding is also very high. Now what happens in grinding is that these abrasive particles, number of abrasive particles are in contact with the workpiece, removes material in minute quantities. Now as it removes material in minute quantities, it allows machining of hard surfaces as well as it allows to obtain high surface finish, and the accuracy is also very high. Now as the abrasives are rotated against the workpiece, these abrasives becomes dull and fractures, resulting in a new cutting edges. That is one possibility. And also sometimes this bonding material, see, abrasives are held using a bonding material in the form of a particular shape. Now this bond sometimes fractures and the abrasives are released. As a result, new abrasive surfaces with the new cutting edges, and likewise softness of the grinding wheel is maintained. But even then, by repeated uses or by faulty conditions, the grinding wheel sometimes may be glazed. So that is called glazing of a grinding wheel. We'll be discussing all this in details in the subsequent slides, but I want to just give you an idea about what you are going to learn in this lecture. So most important, in general, grinding is used when you want to remove a very small amount of material and give it a very good finish and obtain a high accuracy of the workpiece. So normally other machining processes remove the maximum volume of material and then it is finally finished by the grinding processes. However, in modern grinding technology, there are certain technology available. Grinding is also used for removing a large volume of material by a process called creep feed grinding. So we'll be discussing creep feed grinding later on in the next lecture. So, okay, now here you can see here the abrasive grains are held together by the bond material. You can see the bond material, various types of bond materials are there for holding the abrasives in the particular form that is required or particular shape that is required. You can see sometimes this bond material fractures and releases the abrasive grains and new grains will surface. And sometimes the abrasive itself fractures and forms a new cutting edges. And sometimes the contact of the abrasives results in abrasion and diffusion and many other such wear mechanisms resulting in adhesive wear, and you obtain a flat surface here, so resulting in what we call a glazed surface. So all these phenomena occurs during the grinding process. So this figure I have taken from this book, Kalpakja Smith, 6th edition, Pearson Education, and this is a special Indian education of which I am also the editor for the SI matriculation of this particular book in Indian edition. So here, if you look, this is a beautiful picture. This again I got this from this particular book. Here you can see the abrasives are of various sizes and various shapes, and you can see these black ones are the workpiece material that is stuck between the abrasive grains, and you can see the space varies. Okay, so this is a particular aluminum abrasives A46J, and the bonding material is vitrified bond. And if you look at this figure, this is a micrograph. You can see this is the negative rake angle. So you can see the rake angle is negative here, and this is the shear angle, which is a very small shear angle you can see here, and this is the chip which is flowing, and this is the abrasive particle. The outline of the abrasive particle is visible to you. So you can see it's a negative angle here. So this is a beautiful picture, and you can see, notice this is a flat portion here and the bottom side, and this is one of the reasons where the grinding specific energy is high and the forces required in grinding is also high. Okay, so forces required per unit volume is also high because of this wear flat. In the next slide you will see the wear flat here. This is the wear flat, and you can see this is negative angle, this is the chip, and this diagram is redrawn here basically, and this is the shear angle. And unlike conventional machining, you can see there are ridges, and basically we are plowing the workpiece surface in minute quantities. We are plowing the workpiece surface in minute quantities here. Again, this figure is taken from this particular book. Grinding wheels are available in various sizes and shapes depending on the requirements. So you can see there are some shapes in front of you. It may be a disc grinding wheel, it may be a cylindrical grinding wheel, it may be a flaring cup, it may be grinding wheel with blade, a disc type grinding wheel, cup type grinding wheel, recessed grinding wheel. So various types of grinding wheel are there. Sometimes the edges are tapered for to match the in between angle of a thread. So for thread grinding is also there. For gears grinding is also there. Involute profiles is also available. You can customize the shape of the grinding wheel for a particular application also. So for various applications we use various shapes of the wheel. These are some of the shapes. You can see tapered, disc type, recessed two side, straight, cylindrical, straight cup, flaring cup. So various shapes has various applications. I am not going into the details of that. Okay, so one very interesting thing is the phenomena of grinding is pretty similar to that of milling machine. because, or in milling process. In milling, there is a rotating wheel or rotating wheel type cutter which is rotated at high speed against the workpiece, normally against the workpiece. So workpiece is fed to the wheel, and the process is very similar. It contains cutting edges at the periphery or maybe at the face. In milling, same thing happens in grinding also. The abrasives may be at the periphery or maybe at the surface or the face. So face is rotated against the workpiece, or the periphery of the grinding wheel is rotated against the workpiece. And each of this abrasive is a multi-tooth cutter. In milling also it is a multi-tooth cutter or multi-point cutter. So here the number of abrasives removes material in minute quantity. So there is very similarity, much similarities are there, but there, in spite of the similarities, there is differences. The grinding wheels, the abrasives are much smaller, and the chips that is formed are also very minute compared to the chips that are formed in milling machine. The cutting speed or the speed at which the grinding wheel is rotated is much higher than the cutter speed of in a milling process. In a grinding wheel, the abrasives are always negative, and it is high negative, almost minus 30 to minus 60 degree angle, negative rake angle for the abrasives, which is not there in milling machine. And one of the phenomena, very interesting phenomena, is the self-sharpening phenomena in grinding wheel. Grinding wheel normally self-sharpens by fracturing of the grains or fracturing of the bond. So that phenomena is not there in milling. So these are some of the similarities and dissimilarities of milling and grinding. Okay, with this we move with various variables that are important in defining a grinding wheel and in choosing a grinding wheel for a particular problem or particular process. The grinding wheel normally consists of the abrasives. Abrasives can be of various types. What are abrasives? Abrasives are hard particles which actually does the cutting in grinding. So these hard particles are normally aluminum oxide, silicon carbide, diamond, that is polycrystalline diamond, or cubic boron nitride. So these are the common abrasives that are used in grinding. Now these abrasives are or given a shape using a bonding material and held together by a bonding material. Now what are these abrasives? Each of these abrasives will be discussing. So first abrasive that we will be discussing is aluminum oxide. Aluminum oxide is normally a general purpose abrasives which are much tougher compared to that of the silicon carbide, but are less hard compared to that of silicon carbide. So these are normally available in two colors depending on its purity. One is gray and one is white. The gray one is more generally used and are used for grinding of high tensile strength steel alloys, whereas the white one is used for heat sensitive steels. The white one is more friable. Friable means it releases the grains more easily, or the grains break more easily, fractures more easily. It may be a fused aluminum oxide or unfused aluminum oxide, and it is denoted by letter A. Now, how these aluminum oxides are formed is basically aluminum oxides are formed by bauxite ore. Bauxite ore are mixed with coke and sawdust, etc., and heated in a furnace to form a rock-like mass. So this rock-like mass so formed is washed and crushed to obtain sharp edges of the abrasives. Therefore, it is crushed and then sieved for differentiated for different size using sieves, which are used in the grinding wheel manufacturing. So aluminum oxide is normally a general purpose abrasives that we use in grinding. So aluminum oxide is followed by silicon carbide, which is denoted by the capital letter C. Silicon carbide is harder than aluminum oxide, and they are available in two colors depending on various factors like purity, etc. Black and green. The black is normally used for grinding of cast iron and non-ferrous alloys like aluminum, copper, magnesium, brass, etc., etc. And also use this type of black wheels are also used for grinding of non-metallics such as ceramics and gemstones. Whereas the green one is mainly used for tool grinding, tool and cutter grinding of cemented carbides and also high-speed steel. Silicon carbide is formed or manufactured by pure white quartz. Pure white quartz is mixed with coke, petroleum coke, and other materials, and then heated in a furnace. This is called synthesizing of coke and sand. So again, the process is similar to that of manufacturing of aluminum oxide. We form a mass, crystalline mass is formed, which is crushed, and then shipped for different sizes. So likewise, silicon carbide is also made. Then other two more exotic abrasives are cubic boron nitride, which is normally reserved for very high strength steel, like high speed steel, tool and die steels, hardened cast iron, and stainless steel. Then we have diamonds. Diamonds are normally not used for ferrous material, because diamond has carbon, and diamond has a high affinity for carbon, and it changes the properties of the ferrous materials. Therefore, it is used for very hard steel, rarely used, and cemented carbide and aluminum oxide cutting tools. It may be glass, etc. For this type of materials, we use diamonds. So these are the abrasives that are used, and you can see the relative hardness. Diamond is the hardest one, followed by cubic nitride, silicon carbide, and then the aluminum oxide. So these are the abrasives that are normally used in grinding wheels. This I have taken from this book, Fundamentals of Modern Manufacturing. It is an excellent book. Author is MP Grover. Okay. So bonds. The next parameter is bonds. Bonds is what? Bonds are those material which holds together the abrasive grains and gives them a shape. So bonds can be of different strength or degree of strength. You have a soft strength bonding, you have a hard strength bonding. So soft strength bond releases the abrasives easily, and high strength bond holds on to the abrasives, and sometimes the hard strength or hard bonding results in a glazing of the wheels. We'll see what is glazing of the wheels in some later slides. So let's start with vitrified bond. Vitrified bond is basically a bond which is made of clay and feldspar mixed together, and it is mixed with the abrasives and poured in a mold, normally in the shape of a wheel, and then heated to around 1200 degrees centigrade to obtain the wheel, to obtain the particular wheel. Now the process of making this wheel is basically time taking. So for making large wheel, it takes large amount of time, and it is very difficult to make large wheel using vitrified bond. However, vitrified bond is the most general purpose bond that is used as a bonding material in grinding wheel manufacturing, and it is not susceptible to oils or acids or water. It can perform its work even in presence of water, oils, or acids. But it has a disadvantage that it is very poor, exhibit poor shock resistance properties. So it is denoted by, vitrified bond is denoted by letter V. Next bond is resonant bond. Now resonant bond is basically used for high speed operations. It is used for finishing operations, and it is also used for rough grinding operations and for cut-off operations. It is susceptible to water. That means it will soften if it is exposed to water for extended period of time. And it is denoted by letter B. It is basically a phenolic resin, or phenol formaldehyde is one of the common type of resonant bond, which is mixed with the abrasives and heated, mixed with the abrasives and placed in a mold, and then heated to about 118 degrees centigrade to obtain the bond. And then we have silicate bond. Silicate bond is basically water glass or sodium silicate, what we know as water glass. This is mixed with the abrasives and again placed in a mold, heated to around 240 degrees centigrade or around 260 degrees centigrade to obtain the grinding wheel. Now it gives a cool cutting. That means it gives a cool cutting action. That means it does not get heated readily, and under wet grinding, the sodium silicate becomes soda and acts as a lubricant. Okay, and the making of large wheel is easier by this particular process. Is denoted by letter S. Now, select bond is an organic bond used for grinding wheels, and it is used for high-speed operations for parts such as steel rolls, camshaft, crank pins, and then they are normally not used for heavy-duty grinding operations. It is denoted by letter E. Now, why I am indicating the letters, because this will be used for specifying the grinding wheel. So these letters are important for you to know. Each letter has a particular significance. Now, rubber bond is denoted by letter R. It is extremely tough and strong bond and normally used for cut-off wheels. Rubber bond is also used as a support wheel it is used for driving wheel in centerless grinding. We'll know what is centerless grinding later. And oxychloride bond is basically oxide and chloride of magnesium, and these are used in this grinding operation. It gives a cool cutting action, but however it should be done dry and it is susceptible to the action of conventional cutting fluids. It is denoted by letter O. So these are the various bonds that are used for aluminum oxide and silicon carbide. However, for bonding material for diamond and cubic boron nitride is normally metals, and brass is normally used for cubic boron nitride and diamonds. However, this bond, vitrified bond, silicate bond, rubber bond, resonant bond, shellac bond, oxychloride bond, etc. are used for bonding the aluminum oxide and silicon carbide, which are most conventionally used. Again, this table I have taken from the MP Groover book on modern manufacturing. Okay, now the abrasive size. Size is also very important. The small size or fine size is used for finish, high finish, and for grinding hard materials, whereas coarse size is used for rough grinding, removing maximum volume of material, and for grinding soft or ductile material. And fine finish gives, fine abrasives will give fine finish. Okay, now how do you obtain this size? This size is determined by the screen opening through which the abrasive grains pass. And normally the number of the nominal size indicates the number of openings per inch in the screen. Suppose a abrasive grain passes through 55 openings per square inch and it does not pass through 65 openings per square inch, then the abrasive grain will be denoted by 60. So it passes through 55, does not pass through 65, it is given a number 60. Okay, so higher the number, finer the grain. The higher the number, finer the grain. So which basically means the number of openings. If the number of openings per square inch increases, that means it allows only very, very fine grains to pass through it. Okay, so this number normally varies from, I think, around 6 to around 1000 or 8 to 1000. And grinding wheel grade. Okay, this is also very important. The bonding material may be holding the abrasive grains very tight to give a very hard wheel. So it will designate that type of grinding wheel as a very hard grinding wheel, or it may be releasing the abrasives very easily. So those are called soft grinding wheel. So depending on how it holds the abrasive, the wheel grade is determined. Now, wheel grade may be soft from A to H, denoted by A to H, medium denoted by I to P, and hard denoted by Q to Z. So Z being the hardest. Now the problem with the hard abrasive wheel grade is that it does not release the abrasives quickly and becomes dull very quickly. Whereas soft wheel will release the abrasive very easily. However, the wear is also very high in softer wheels, whereas the wear is less in harder wheels. So softer wheels are normally used for machining hard materials, whereas hard wheels are normally used for machining soft materials. Grinding wheel structure. The relative spacing between the grain also influences the grinding process. Now, if the relative spacing is more, that means it can accommodate large amount of workpiece material which is machined or chipped off from the from the workpiece. So open structure is normally used for machining soft and ductile material and for rough grinding, whereas for fine finish and for machining hard material, closed structure or denser structure is used. The structure is denoted by, I think, 1 to 15, 1 denoting the denser and 15 denoting the open structure, more open structure. So this type of structure is obtained. You can see there the various pores are there, so you can have more space. The more space means it allows the chips to accommodate. It allows the chips to accommodate. Now there is a phenomena where large number of chips are accommodated and the grinding wheel does not cut properly. That phenomena is called loading of the wheel. That phenomena is called loading of the wheel. We'll be seeing that, or we'll be learning about that in the subsequent slides. Okay, now how do we specify a grinding wheel? Grinding wheel is specified universally by this particular sequence. First we denote the abrasive type, followed by abrasive grain size, followed by the grade, structure, and then bond. And there may be a prefix and there may be a suffix depending on the manufacturer. But these 5 parameters are important while specifying a grinding wheel made of silicon carbide and aluminum oxide. Diamond and cubic boron nitride grinding wheel are specified slightly different manner. But this silicon carbide and aluminum oxide grinding wheels are specified by this manner. So first we'll be using the abrasive type. So it may be A or it may be C as shown here. It may be aluminum oxide or it may be C. And then the grain size. The grain size varies from 8 to around 600. 8 to around 600. The grain size varies. It may be up to 1000 also, normally around 600. So this size varies accordingly. 36 is a medium size grain here in this particular example, A36 L5V. So L is the grade. It is again a medium grade. It is neither soft nor hard. And structure 5 is again a dense structure, fairly dense structure. Okay, and beautified bond is a general purpose bond. There are various types of bond there. This particular is a wheel. It's designated is a very general purpose wheel. So you can see the same example here given. It is underlined. The particular example is underlined here. This is the specification used for designating cubic boron nitride and diamond. It's pretty similar. Abrasive type, grid size, grade, diamond concentration is also mentioned here. Bond and bond modification and the diamond depth. So all these are specified in a in specifying diamond and cubic boron nitride. So we are not going into discussions on this. Okay, now how do we go about selecting a grinding wheel? The first important criteria that we will be discussing is the material to be ground. What is the workpiece material? Now workpiece material defines several factors like abrasive grains. What type of abrasive grains? We know aluminum oxide are used for the high tensile strength steels or general purpose steels, whereas the silicon carbide is used for cast iron, for non-ferrous materials like aluminum oxide, magnesium oxide, etc. And silicon carbide is also used for machining cemented carbides, whereas if it is a high strength steel like tool or die steel, we will be using cubic boron nitride, and likewise for very hard materials we will be using diamond. If it is non-ferrous and very hard material, we will be using diamond. If the material is hard, we will be using fine grains. If the material is hard, we will be using fine grains. And if the material is soft, we will be using coarse grains. If the material is hard, we will be using close spacing. Structure should be close or dense structure. And the grade should be soft grade, because you want to release the abrasive grains easily because it is a very hard material. Whereas if the material is soft or ductile material, the grain spacing should be open spacing, because you will be removing large volume of material, and the grain and the bond may be hard. The grade may be hard grain, because it will not be. You don't want the abrasive grains to be released readily because you are machining a soft material. And the nature of grinding operation. If you are using a fine finish, if your objective is to obtain a fine finish, you should be using fine abrasive grains, and the bonding material should be select bond, rubber bond, resonant bond. This type of wheel should be used. And for rough grinding, you should be using vitrified bond and coarse grains. Area of contact is also important. The width of the wheel you are using. If the area of contact is more, you should use open structure, coarse grains, and harder wheels should be used. Condition of the machine. If the condition of the machine is old, so there will be large amount of vibrations, you want a harder wheel. And the grinding wheel speed. For higher speed, you should be using select bonded, resonant bonded, and rubber bonded wheels. More than 2000 meter per second. Okay, per minute rather. Okay, and the grinding pressure is also important. If the grinding pressure is high, the infeed is high, then it is better to use harder wheels, because under high pressure you don't want to release the abrasive grapes easily, so you require a hard wheel. So these are the criteria of based on which you will be selecting a grinding wheel. Okay, these are some of the these I have taken from the Kalpagyan book. You can see some of the grinding wheels with the names and the specifications for different types of materials. Okay, so with this we will be discussing the mechanism of grinding process. So the cutting and grinding wheel is obtained through simultaneous engagement of number of abrasive grains, and you can see the distance here. The distance, the chip, the length will be the distance between the two grains, and as it passes out, so by centrifugal force, the chip will be thrown forward, or due to the flushing agent, the chip will be thrown forward. So this is the mechanism. You can see A is denoted by, I will be using T to denote the thickness, and this is the contact length, and this is the diameter of the grinding wheel, and this is the peripheral speed with which the grinding wheel is rotating, and this is the feed velocity. This is the velocity with which the grinding wheel is rotating, and this is the feed velocity, the velocity with which the workpiece is fed. Okay. And this figure I have taken from this journal, Journal of Production Engineering, and the author of this particular paper is Investigation of Cutting Forces in Creep Feed Grinding. The total cutting forces is summation of force required for deforming the material and force required to overcome the friction, because there is a wear flat you have seen earlier, so there will be a large amount of friction which has to be overcome by the grinding wheel. So therefore the force required is also large compared to conventional processes, machining processes, and the total force is summation of each individual forces encountered by each grain, and it is summation of 1 to Na. Na is the number of active grains. So we'll find out the average number of grains at a particular point of time is engaged with the workpiece, and the force has to be is basically a summation of all the forces acting on the grains, active grains rather. And the force that is acting on the wheel or on the workpiece can be divided into two categories: the tangential component and the normal component. The normal component is normally around 30% higher than the tangential component. So Fn is slightly larger, or around 30% larger than the tangential component. So here you can see this is the Ft and this is the Fn. So Fn is the normal force applied by the grinding wheel on the workpiece, and this is the tangential force applied by the wheel on the workpiece, Ft. And this is the contact length, this is the depth. And this figure I have taken again from this particular paper, where they have given the schematic diagram of the setup they have used to find out to measure the forces. They use the dynameter to measure the analog data is taken and is converted into digital data and stored in the computer. So dynameter is used to measure the forces, that is normal force and the tangential force. And their findings are given in these two figures. You can see as the depth of cut increases, the normal force and tangential force also increases. However, you can see at first there is an increase in this ratio, normal force tangential force, then this ratio decreases. So the rate of increase of the tangential force increases with the depth of cut compared to that of the normal force. And again, the normal force here decreases with increase in the wheel speed. So normal force decreases and the cutting force, the tangential force increases here. These are the findings of this particular research, which is published in Journal of Production Engineering in 2015. Okay, so energy that is required in grinding is also higher compared to the conventional machining processes, and the specific energy is basically sum of specific energy required for chipping, specific energy required for plying, and specific energy required for sliding. So why it is higher? Three reasons you can associate for this higher specific speed is size effect, wear flat, and chip morphology. So what is the size effect? See, grinding here, in grinding we remove the material in minute quantities. The thickness is very small. Now in this small thickness, the deformation, the probability of the deformation or dislocations of the material is very low. So therefore, the grinding, the deformation has to be carried out by breaking the metallic bond, actual metallic bonds, and therefore the grinding force required is much higher, around 10 times higher actually. So that is the size effect. And then wear flat is there, the grinding force, the grinding has to overcome the frictional force associated with, therefore also the grinding energy required is also high, and therefore, and another reason is that it is machining with a negative rake angle, and machining with a negative rake angle, the shear strain are also large. So therefore the specific energy that is required in grinding is also high. So these are the values of the specific energy required in grinding energy. So this I have taken from this particular book, or 6th edition, or you can say 4th edition, same thing. So calculation of the grinding force. So how to calculate the grinding force? The grinding force to calculate, you require to measure the material removal rate. You can measure the material removal by this value. You know the depth of cut, you know the width of cut, and you know the feet rate with which you are machining. So if you multiply these three terms, you will get the material removal rate. Once you have the material removal rate from handbook, you can find out like this table, you can find out the specific energy for the particular material you are cutting. It's given rough estimate of the power that is you are getting. Power is equal to specific cutting energy into the volume of material removed per unit time. So that will give you the power that is being consumed, a rough estimate of the power that is being consumed, and that is equal to the torque that is applied by the wheel and the angular speed of the wheel. So torque is applied, basically you can measure the FC, or if you want to find, I'm interested in finding out the FC. So torque is basically FC into the radius, and this is equal to twice pi n. This is the angular speed. So U into MR is equal to FC into D by 2 into twice pi n. So all these parameters are known to us. So I can find out the FC, the tangential force or the cutting force, or FT, FC or FT, and the normal force can be found out to be approximately 30% higher than the cutting force. So like this you can calculate the grinding force. You can see here, this is the depth of cut and this is the contact length. Now this contact length changes actually. This is a static contact length, there is a dynamic contact length or kinematic contact length also, because as you are rotating, there is a contact, it is moving forward. So in a second it comes to this, the contact length increases. So therefore the contact length actually varies. So this is a contact length of the chip. This is thickness, this is the depth of cut we are taking, this is the depth of cut we are taking, and this is the width of the cut. And you can see we are plowing, so it is normally like this. The shape of the chip is normally like this. The cross section of the chip is normally like this, and this is an average thickness. So the speed of grinding wheel is equal to the peripheral speed, or Vs, is equal to pi dn by 1000, where d is the diameter of the grinding wheel and n is the RPM with which it is rotating. So material removal rate already we have discussed, and it can be shown that if Fr is very less than the speed, L is equal to d into d. This is for cylindrical grinding, and this is for surface grinding, and these are for cylindrical grinding. These two expressions are for external cylindrical grinding and internal cylindrical grinding. Okay, so process parameters, the various process parameters are there: cutting speed, feed rate, the grinding wheel diameter, the workpiece diameter in case of cylindrical grinding, the depth of cut, the length of contact, the average chip thickness. So one thing is very important. See here, the grinding wheel is currently center here, and in next instant it is here, depending on the feed rate. Now LK is called the kinematic contact length. This is called the kinematic contact length. Now let's see. This is the this travels from here to here if there is no feed. Okay. Now this distance traveled per unit time is the peripheral speed, that is Vs. That is the Vs or Vc, what is saying. So the time required to move from without any feed is from here to here is this Lg by Vc. However, if there is feed, so by the time, say within same time, this point, it should reach here, but it reaches here because of the feed. So that is equal to, this distance is equal to Vft, that is the feed velocity in this direction, or Fr I have defined as Fr feed rate. So this is Fr into Lg by Vc. So you can calculate accordingly this He. He is the equivalent chip thickness, which can be calculated as Ae. Ae is the Ae, and these are given here. I'll show you in this figure. This is your AP, and this is your back engagement. This is the depth of cut. Ae is basically the depth of cut. Lg is geometric contact length. So there is a geometric contact length and there is a kinematic contact length. And this is the H equivalent thickness. Okay, how do grinding wheel wear? It is also important. This I have already discussed. The three ways it wears. Grinding wheel fractures and it wears, and new grains are obtained. And sometimes due to normal abrasions and other factors, attritious wear takes place and it becomes flat. So this is another method. And sometimes the bond fractures and again grains are released and new grain surfaces. So like this, the grains wears. And it is obviously grinding wheel is wearing or will wear more rapidly compared to other cutting tool wear in other conventional processes. So here the wear normally starts. Initially there is a rapid wear, then there you have a steady up state, and then finally there is a rapid wear also. So this is the graph with the volume of material removed and the wear. And there is a thing called grinding wheel ratio. This is basically the volume of material removed and the volume of wear. So this indicates a sort of an efficiency, and the value varies from 2 to 200. However, it normally around 95 to around 150. It varies within that particular region, and there are various factors on which this depends: the type of wheel and the workpiece material, the grinding fluid used or not, the process parameters like depth of cut, speed, etc., etc. Now, if you increase the speed, you can see that the grinding wheel ratio increases. The grinding wheel ratio increases. Okay, there is an increase in the grinding wheel ratio, or the grinding wheel wear decreases. So here basically you will see, if you increase the speed, it decreases. The grinding wheel ratio increases and the surface finish increases here. You can see this, the surface decreases, so surface finish increases here. So, but however, after certain speed, if you go beyond that, then it is detrimental. So here the surface finish also is distorted, and the grinding wheel also ratio is also decreasing. Okay, so another very important factor regarding the grinding wheel, two aspects, is wheel balancing and wheel mounting. These two are very, very important. When you are going for grinding, you should mount it very carefully, and you should test the grinding for any kind of internal fracture or not. So normally we use a wooden mallet and strike the wooden mallet on the grinding wheel, and by the sound of the grinding wheel, if it gives a clear ringing sound, ting sound, that means the grinding wheel is perfect and sound. If it is given dull sound, that means there is some internal crack, and that cracked grinding wheel should not be mounted. So it is very important to test the grinding wheel and mount it properly. Mounting requires, normally it is done in the foam and the foreman normally does the grinding wheel mounting in any kind of machine shop. So grinding wheel mounting is very, very important. I have listed out some steps how to mount the grinding wheel. You can go through this. So these are important, and balancing also is important. Out of balance will may cause accidents. So it has to be balanced properly before it is mounted. Grinding wheel has to be balanced properly before it is mounted. So wheel balancing and wheel mounting is two important aspects in grinding process. Okay, now other aspects like grinding wheel glazing. See, by repeated using, the grinding wheel becomes dull. Mainly it happens when the grinding wheel is hard. Even if it is not hard, ultimately it will become dull, and the condition of the wheel is called glazed. And sometimes for open spaced grinding wheel, chips get lost between the grains, and once the chips are lost completely, it will not cut properly. So such a wheel is called loading. So this is called glazing, loaded wheel. So this process is called glazing and loading. So how to overcome that? By process called dressing. Loading and glazing can be overcome by dressing. Dressing, we use a diamond point tool, and basically we remove a certain volume of material from the grinding wheel so as to remove the worn out abrasives, and new abrasives are released. So this is used like this. You can see the grinding is rotated against a abrasive, against a diamond point tool, and sidewise it is moved at an angle, and it removes a layer of material from the wheel to release or to bring out new abrasive grains and to remove the workpiece material that is stuck between the grains. Another phenomenon is called truing. Sometimes by using faulty use, so the roundness of the wheel is compromised. Now that is also done by same tool, diamond point tool, and by similar process, and you can correct the roundness of the wheel, and the process is called truing. So this is a graph showing the coarse grain, medium coarse grain, and fine grain, how it affects the roughness. You can see the roughness decreases initially high for coarse grain, and for fine grain the roughness is obtained is fine and initially, and then the roughness increases with the number of workpiece being done. Similarly, the power required in fine grain is also higher. Initially it will very, very high, then decreases, and then again increases. So similarly for coarse grain the power required is less, however it increases as the number of workpiece increases. So with this, this I have taken from this book, Principles of Modern Grinding Technology, 2nd edition, 2014, by W. Brian Rowe. So in the next lecture, we will be discussing about different types of grinding processes. Thank you for watching this video. If you have any doubts, please contact me through the comment section, or you can email me. Thank you.